Hello student. So in this video uh, I'm going to discuss about the topic Carnot engine and the Carnot cycle. Okay, and I also find the efficiency of the Carnot cycle. So this video lecture is one of the most important video lecture in our thermodynamic chapter. So to understand that this video you have to follow my previous video. Okay, so first I can discuss very briefly Carnot engine, then I can find the cycle of the Carnot cycle and also find the efficiency. I will find the efficiency of the Carnot cycle. So this is a step-by-step process. I just mention the important highlighted points. Okay. So first heading in this topic is you can write the Carnot reversible engine. Okay. Carnot reversible engine. So in the last video I already discussed what is the reversible. Reversible means if I get back the it means my initial and final position are same. There is no if there is no loss of any energy, then we can say this is the reversible process. Okay, so here it is a Carnot reversible engine. So if it is reversible, it means we are getting the 100% efficient engine. Maybe it is not practically possible, but theoretically you can see you can get the 100% efficient engine. So you can write just basically it is basically a reversible engine with 100% efficiency. With 100% efficiency. Okay, so in that case it means there is no loss factor. So basically it is a 100% efficient engine. Okay, and also we can write it here that in reversible the one more condition is that the it is the ideal engine. Okay, the ideal engine operating between two temperature. Ideal engine operating between two temperature should be a reversible engine. In reversible engine it is also it should be operating between two temperature. Why? Because suppose my this is initial this is a one temperature, so it may go from this point to that point, and again it come to return to that point to that point. So maybe here the T1 and T2, so it only operate between two temperature. This is the initial temperature. If it is in one cycle, in full complete cycle, this is one temperature, this is T2 is another temperature, and again it return back to the temperature T1. Okay, so it is operating between two temperature only. And already we said that in reversible engine, why you can get only this two temperature, because there is no any loss factor. Okay, because no dissipative effect, because there is no loss factor, there is no loss of any energy, there is no loss of any temperature. That's why it is operating between only two temperature in case of reversible, and it is an ideal engine. So what is basically the Carnot reversible engine? Carnot reversible engine basically give the 100% efficient result. But what happened in our second law of thermodynamics say that it is not possible to get the total heat into work. But this is the ideal engine. It may be practically maybe it is not possible, but in that case it is the ideal engine and it give the 100% efficient work. And it is the reversible engine also. So in reversible means it must operate between two temperature, and there is no any loss factor. It means we can get the almost, it means we can get the, not almost, we can get the 100% input. Okay. Now, after the Carnot heat engine, now we can discuss the Carnot cycle. Okay. So what is the cyclic process of the Carnot? How we get this kind of 100% efficient output? Okay. So some process may be there. So next heading we can write it the cycle of process in a Carnot engine. Okay, so this is the cyclic process in a Carnot engine, in which process we can get this 100% efficient results. So before discussing this, I am just writing a rough diagram, and you must understood this. Suppose this is engine. Okay, and this is, and this is Q1. This H means hot, and the temperature is T1. It is the mode temperature. Okay, and this part is also T1. This is the engine. This part is T2, and this is Q2. We can say this is the cool part, and the temperature is T2 in that part. Okay, this is heat supplied, this is heat released. So here the condition is T1 greater than T2, because this is the hot part and this is the cold part, so obviously T1 greater than T2. And it is a cyclic process, that's why the process keep continue. It is a continuous process. Okay, so you can understood this diagram. Okay, so the first process is, I'm just writing here, the first process is expansion, isothermal expansion. First process is isothermal expansion. So this is this part is, we can say this part is the first step. We can say the step 1. Step 1 is the isothermal expansion. So what is isothermal? Isothermal, we say that it is a very slow process. Okay, and in that case isothermal, our T is equal to constant. So you can see the Q, this is the hot, that engine absorbed the energy. Okay, but the process is very slow, that's why our temperature, this T1 and T1 is same in case of isothermal. The process is very slow, that's why our this both T1 is same, and it is isothermal expansion, it is gaining energy. Okay, so the first step is isothermal expansion. From this step we can this engine absorbs some heat, and the temperature from this and this part is same. The step 2 is adiabatic expansion. So in adiabatic expansion, our this T and T, adiabatic expansion means there is no any incoming and outgoing heat is there. Okay, so there is no use of any heat, but it is the expansion. Okay, so expansion, that's why maybe its volume may increase, and due to this thing, its temperature may reduce to T2. Okay, so in adiabatic expansion, T1 2, we can get that T1 to T2. And also in adiabatic it is a non-conducting wall. Okay, so lots of things may happen, and due to this non-conducting, and the process is very fast, and it is an expansion process, that's why its temperature reduced to T1 to T2. The third process, again from T2 to T2, and this is the step 3. So in this step it is a isothermal compression. It means it compress, it release the energy, it release the energy, but same the process is very slow. That's why our T is constant. Same the T is constant. This T2 and T2 are same, but it release the energy. Okay, so we can get the cold part. This part is hot. The first part, this is the hot part, and this is the cold part. Why? Because it released the energy. So the third process is the isothermal compression, and the fourth is adiabatic compression. Adiabatic compression means it compresses and it is a repeat process. So again return to T2 to T1. When I compress anything, it pressure may increase, its temperature may increase. So again it return back to T2 to T1 to T1. Okay, so again the process, again it starts keeps continue with the process. So there are four process, and in fourth step: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. So now I'm writing this in proper manner. So in the first step, you can write the first step 1 is heat absorbed, heat absorption, but no temperature gradient, no much difference between temperature, because it is isothermal, so there is no change in any kind of temperature, and whatever the change, it is the negligible change. Okay, and engine absorbs Q1 and T1. So in the first process, it absorbs the energy. Okay, now step 2 is adiabatic. So you can write it is a temperature T1 to T2. Why? Because in that case we are not applying any extra heat, but it is adiabatic expansion. Okay, expansion, it is adiabatic expansion, that's why its temperature may reduce. Okay, the condition is that T1 greater than T2. The step 3, heat release. Okay, so it is a isothermal compression. So but in case of isothermal, our temperature must be same. And the step 4, adiabatic compression. So due to the compression, again its temperature increase T2 to T1. Okay, T2 to T1, and again the same, the process again starts continuing or repeating. So there these are the 4 steps needed to get the Carnot cycle, or to get the 100% efficient engine. Okay, and this one cycle, this all the 4 step cycle, we can say that this is the Carnot cycle. So one cycle of the Carnot's engine is a Carnot cycle. So what are the cycles? First is isothermal expansion, the second is adiabatic expansion, the third is isothermal compression, the fourth is adiabatic compression. All these four are together in one cycle. We can say that this is the Carnot cycle. Okay, so now the next we are going to find the efficiency of the Carnot cycle mathematically. Okay, we can find the efficiency of the Carnot cycle. So just write the heading Carnot's cycle. So this is the mathematical derivation. So first we know that isothermal expansion of the gas. So first process is the isothermal expansion of the gas. So we know that work done by the gas. So already I derived this the work done of the isothermal and adiabatic. So what is the work done? Is I can write W1 because they are forced process, mu R T T1 P2 V1 V2. Okay, this is the V1 V2 and I can write it here P1 V1 T1 to P2 V2 T1. So this is the change. This is the formula mu r T1 ln V1 minus V2. And in that case our this T and T must be same, but our pressure volume may be changed from step 1 to maybe in step 2. Next we can write adiabatic expansion of the gas. So work done can write directly W2 equal to R gamma minus 1 and T1 minus T2. So in that case what happened? In that case our P2 V2 T1 to P3 V3 T2. Okay, so this is the process of adiabatic expansion. Third, isothermal compression. So we can write work done is equal to W3. So it is a compression, so you can write it like this: mu r T2 ln and it is V3 by V4. So in that case it changes like this: P3 V3 T2 compression, that's why, and P4 V4 and T2. Due to the isothermal the temperature is same. And the step 4 is adiabatic compression. So work done is we can write W2 R gamma minus 1 T1 minus T2. So in that case it is changes P4 V4 T2 and P1 V1 T1. You can see again we can come to the first step. So now I can write all the four work done formula in this Carnot cycle. Then what is the next is total work done. Now I am going to find the total work done in our Carnot cycle. W1 plus W2 minus W3, these are the compression, minus W4. So after putting all the work done we can get the final result is just like this: Q1 minus Q2. So I can write R T1 minus T2 log V2 by V1. So this is the work done, total work done in case of Carnot cycle. So this is the total work done in our Carnot cycle. Now our next aim is to find the efficiency. Okay, efficiency. We can represent the efficiency eta equal to total work done by the Q1. So what is this Q1? You can write the amount of heat received. Okay, Q1 is the amount of that received from hot reservoir. This is the Q1. Okay. So now what is the next step? Next step is what is the total work done. I can just put the value R T1 minus T2 log V2 by V1. I can just put this total work done W. Then what is the Q1? R T1 log V2 by V1. So what will be our next step? Our next step is eta equal to T1 minus T2 by T1, because other terms are getting cancelled. So ultimately our eta equal to 1 minus T2 by T1. So this is my formula for efficiency. Okay. So this is the formula for efficiency. So first I discussed the Carnot reversible engine, and then I discussed the Carnot process, cyclic process. Then I put all this work done formula into the Carnot cycle, and I can get the total work done and the efficiency. So these formulas are very much important for numerical purpose and also for the derivation purpose. Now how can I represent this Carnot cycle graphically? So just I can write it here. Carnot's cycle graphically. Okay, so this is P, this is V. So this is my first process. I can write P1 V1 T1. So this is the isothermal. So isothermal process, I already said it is not that much sharp. Okay, this is isothermal. This is isothermal expansion. So in isothermal means our temperature must be same. So this is in the second process P2 V2, but temperature is T1. Why? Because our temperature is same and the process is slow. That's why it is not that much sharp. Slope is not sharp. Okay, but our pressure getting reduced here and volume getting increased, so it neutralize each other. That's why our temperature is same. Next I can get, this is the adiabatic expansion. So this is my adiabatic expansion, and you can see this is the very sharp changes, and the slope is very sharp. So that's why what happened, our pressure getting reduced and volume getting increased, very sharp reduced na. That's why my temperature is also getting changes in that case. So this is adiabatic expansion. Now again the next process is isothermal compression. So again it is isothermal compression, very slow process, and our temperature must be same. That's why we can write it, it is just like this, P4 V4 and T2. Why the same temperature? Because it is the isothermal. Isothermal means our temperature must be same. And that the final process is this one. This is adiabatic compression. So again the process is very sharp. You can see this is a very sharp process. Okay, and due to the very sharp process, again its temperature getting rise to T2 to T1. So I can write T1 greater than T2. So T2 to T1. Okay, and again we can get this, the first step P1 V1 and T1. So this is a cyclic process, and this whole process, we can say that this is the Carnot process, and you can represent, or you can also the PV diagram, and this is the Carnot cycle. We can represent it graphically. Reversible Carnot cycle. Okay, and so I think you understood this Carnot engine, Carnot cycle, then efficiency, how we get the efficiency of this Carnot cycle, and how we draw the Carnot cycle graphically. So if you have any doubt, then you can text me, you can comment me, and also you can watch my previous videos to understand this video. You need to follow my previous video also. Okay, so thanks for watching this video. Thank you.